Welcome to Lecture 14, the Algebra of Derivatives, Section 4.1 of the text Advanced Calculus by Patrick M. Fitzpatrick. This is Dr. Gilbert Eyabi. So today we start looking at differentiation. The simplest type of function f from the domain R to the set of real numbers R is one whose graph is a line. For such a function, the ratio f of x1 minus f of x2 divided by x1 minus x2, where x1 is different from x2, does not depend on the choice of the points x1 and x2. We call such a ratio the slope of the function f. So, a function f whose graph is a line is completely determined by prescribing its functional value at one point, say x0, and then prescribing its slope m, and in this case it is defined by the formula f of x equals f of x0 plus m times x minus x0. In college algebra, you were told that the equation of a line is defined as y minus y1 equals m into x minus x1. Well, that is exactly what we just said. Right here, this is your y1, which is f of x0, and that is your m, x minus, in this case, instead of x1, we are using x0. So f of x equals f of x0 plus m times x minus x0 for every real number x. For a function whose graph is not a line, it makes no sense to speak of the slope of the line. So what do? However, many functions have the property that at a certain point on their graph, the graph can be approximated in a sense that we will soon make precise by a tangent line. For such functions, the slope will vary from point to point, and when we determine the slope at each point, we have very useful information for analyzing the function. This is the basic geometric idea behind the concept known as differentiation. So, subsection 4.1.1, definition. An open interval I equals AB, A strictly less than B, that contains the point x0 is called the neighborhood of x0. From time to time, I may use the phrase the epsilon neighborhood of x0. That means the very small neighborhood, the very small open interval that contains x0. That will be the epsilon neighborhood of x0. Subsection 4.1.2, tangent lines and derivatives. For a function f from the interval I to the set of real numbers R, where I is the neighborhood of x0, observe that for a point x in I where x is different from x0, the slope of the line joining the points x0, f of x0, and x, f of x is given as f of x minus f of x0 divided by x minus x0. And if we look at the picture, here is what we're talking about. So this is the point right there, x0, f of x0, and the slope of the line joining the 2 points x0, f of x0, and x, f of x is given by f of x minus f of x0 divided by x minus x0, tangent lines and derivatives. It is reasonable to expect that if there is a tangent line to the graph f from I to R at the point x0, f of x0, which has a slope m0, then one should have the limit as x approaches x0 of f of x minus f of x0 divided by x minus x0 equals m0. Now this brings us very close to the definition of the derivative, which is known as computing the derivative from first principle or by definition. So, subsection 4.1.3, definition. Let I be a neighborhood of the point x0. The function f from I to R is said to be differentiable at x0 provided that the limit as x approaches x0 of this quotient f of x minus f of x0 divided by x minus x0 exists. So that means the left-hand limit must equal the right-hand limit, in which case we denote this limit by f prime at the point x0 and we call it the first derivative of f at x0. First derivative because we shall also look at second derivatives, third derivatives, and so on and so forth. So we would define f prime at x0 to be the limit as x approaches x0 of f of x minus f of x0 divided by x minus x0. That is known as finding the derivative of a function from first principle or by definition. So if I give you a function and I ask you to find the derivative of that function from first principle or by definition, I expect you to find the limit as x approaches x0 of f of x minus f of x0 divided by x minus x0. But if I ask you to use some of the rules of differentiation, then you can go ahead and use the sum rule, the product rule, the quotient rule, the chain rule, and so on and so forth, and we shall see those later in this class. If a function f from the domain I to R is differentiable at every point in I, R is the set of real numbers, I is an interval. So if f is differentiable at every point in I, we say that f is differentiable. So not just differentiable at the point x0, but differentiable on the entire domain I. And in that case, we call f prime, which is also a function, from I to R, the derivative of f, or to be more precise, the first derivative of f. We would proceed by looking at a couple of examples before we prove a couple of theorems from section 4.1. Example number 1. Find the derivative of f, if it exists, using the definition of a derivative at the points indicated. Again, if you are asked to find the derivative using the definition or using first principle, it means we want you to find the limit as x approaches x0 of f of x minus f of x0 divided by x minus x0. So example 1, f of x equals 8x plus 5, and our point of interest x0 is 3. So f prime at 3 is the limit as x approaches 3 of f of x minus f of 3 divided by x minus 3. I substitute my f of x and f of 3. That equals limit as x approaches 3, 8x plus 5 minus 8 times 3 plus 5 divided by x minus 3. You would observe here that I did not immediately evaluate 8 times 3. And you would soon know why that is the case. If I open up my parentheses, 5 and negative 5 will be gone. I would end up with limit as x approaches 3 of 8x minus 8 times 3 divided by x minus 3. Now I can factorize out my 8, and that gives me limit as x approaches 3 of 8 into x minus 3 divided by x minus 3. This is the reason why I did not simplify 8 times 3. I was getting ready to cancel out x minus 3 and x minus 3. And that gives me limit as x approaches 3 of 8. And that simply equals 8. Therefore, the first derivative of f at the point 3 is 8. And we're done. Looking at the example given in A and the example given in B, it's very easy to see that the first derivative of f for the second example would be m. Let's go ahead and verify that. By definition, let us fix the point x0 in R. Then f prime at x0 is the limit as x approaches x0 of f of x minus f of x0 divided by x minus x0. That equals the limit as x approaches x0. F of x is mx plus b. F of x0 is mx0 plus b. All of that divided by x minus x0. B and minus b are gone. I'm left with limit as x approaches x0, mx minus mx0 divided by x minus x0, and I can factorize out my m, and I'm left with x minus x0 divided by x minus x0, which is the limit as x approaches x0 of m, and that is m. Therefore, for every real number x, the first derivative of f is m. And we're done. Let's look at a few more exciting examples. C, f of x equals 3x squared plus 4. Again, fix the point x naught in R. Then f prime at x naught equals limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught. Replacing f of x naught, we get 3x squared plus 4, 3x naught squared plus 4, all of that divided by x minus x naught. And using simple algebra, that equals limit as x approaches x naught, factorize out the 3, factorize out x squared minus x naught squared, using what we popularly call the power rule or the difference of powers formula. That is x minus x naught times x plus x naught, all of that divided by x minus x naught. By now, you would have realized that our big goal is to find the way to cancel out the term in the denominator, x minus x naught. You cannot go ahead and substitute x naught for x if you have not yet cancelled out the denominator. Otherwise, it's going to vanish and we would have a problem. So we cancel out x minus x naught, x minus x naught. I'm left with limit as x approaches x naught of 3 times x plus x naught. Now I can replace my x by x naught. That gives me 3 times x naught plus x naught, which is 3 times 2x naught, and that is 6x naught. Therefore, for every x in R, the first derivative of f is 6x. And we are done. It almost looks like every continuous function is differentiable. No, that is not the case. In our next example, we would look at a function that is continuous, but it is not differentiable at a particular point. So that would actually give us an example of a function that is differentiable everywhere except at a chosen point. Interesting. D, let f of x be the absolute value function. We want to verify the differentiability of f at the point x naught equals 0. So what we do is recall that the first derivative of f at x naught would exist if the limit exists. And the limit would exist if the right-hand limit equals the left-hand limit. So let's approach this problem in that direction. Limit as x approaches 0 from the right-hand limit of f of x minus f of 0 divided by x minus 0 is the limit as x approaches 0 from the right of absolute value of x divided by x, because f of 0 is 0. So this would be limit as x approaches 0 from the right, absolute value of x divided by absolute value of x equals 1, since x is greater than 0. And the limit as x approaches 0 from the right of 1 is 1. So therefore, the limit as x approaches 0 from the right of f of x minus f of x naught divided by x minus x naught is 1. What happens when x approaches 0 from the left? The limit as x approaches 0 from the left, or the left-hand limit of f of x minus f of 0 divided by x minus 0, is the limit as x approaches 0 from the left of absolute value of x divided by x. X is less than 0 because x is approaching 0 from the left. So absolute value of x divided by x is -1. And the limit as x approaches 0 from the left of the function -1 is -1. So the left-hand limit equals -1. The right-hand limit equals 1. And what does that mean? It means the limit as x approaches 0 of f of x minus f of x naught divided by x minus x naught does not exist. So we have seen an example of a function that is continuous, but it is not differentiable. What if we decide to go the other direction? If a function is differentiable, does it necessarily mean that the function is continuous? Does differentiability imply continuity? We do know that continuity does not necessarily imply differentiability. What about the converse? Let's check that out. Subsection 4.1.4.2 proposition. Let I be a neighborhood of the point x naught. And suppose that the function f from I to R the set of real numbers, is differentiable at x naught, then we can conclude that f is continuous at x naught. Interesting. So the converse is true. Differentiability implies continuity, but continuity does not always imply differentiability. So let's go ahead and prove that if a function is differentiable at the point x naught, then it is also continuous at that point. Proof. Suppose f is differentiable at the point x naught in I. Then the first derivative of f at the point x naught is the limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught. Our goal would be to show that f is continuous. So let's go ahead and do that. Suppose the limit as x approaches x naught of x minus x naught equals 0. To prove that f is continuous, we have to show that the limit as x approaches x naught of f of x minus f of x naught equals 0. In other words, the limit as x approaches x naught of f of x equals f of x naught. As simple as that. So we're going to start with the left-hand side and hopefully arrive at the number 0 and then conclude. So let's do that. Limit as x approaches x naught of f of x minus f of x naught equals the limit as x approaches x naught, simple algebra, f of x minus f of x naught divided by x minus x naught times x minus x naught. We haven't done anything. We just multiplied and divided by x minus x naught. Now, using my product limit theorem or the product property, this becomes limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught times limit as x approaches x naught of x minus x naught. But f is differentiable at x naught. So this first component right here is simply f prime at x naught. And from here, we did suppose that the limit as x approaches x naught of x minus x naught equals 0. So all of this is 0. F prime at x naught is a real number. This is 0. And this real number times 0 is 0. What have we done? We just succeeded to prove that the limit as x approaches x naught of f of x equals f of x naught. Therefore, we conclude that f is continuous at the point x naught. So if f is differentiable at x naught, it is continuous at x naught. Let's look at a couple of other rules of derivatives. Subsection 4.1.4.1 proposition. Yeah, you probably observed that I did 4.1.4.2 before 4.1.4.1. That was intentional. I wanted us, since we had given an example of a function that was continuous but not differentiable, I wanted us to start with the second subsection of 4.1.4, which stated that if a function was differentiable, then it was continuous. So subsection 4.1.4.1 proposition, let n be a natural number and define f of x to be x raised to the power n for every x in R. Then the function f from R to R, set of real numbers, is differentiable and the first derivative of f is given as n times x raised to the power n minus 1 for every real number x. Let's go ahead and prove that using the definition of a derivative. We fix x naught in R, the set of real numbers. F of x is defined as x raised to the power n. So the first derivative of f at the point x naught is the limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught. That is our definition. F of x, x to the n, f of x naught to the n, divided by x minus x naught. Recall, our goal is always to get rid of the denominator. Using our difference of powers formula, which we also call our power rule, x raised to the power n minus x naught raised to the power n factors as x minus x naught times x to the n minus 1 plus x to the n minus 2 x naught plus x naught raised to the power n minus 1, all of that divided by x minus x naught. I cancel out my x minus x naught from both the numerator and the denominator, and I'm left with a limit as x approaches x naught of x raised to the n minus 1 plus x raised to the n minus 2 times x naught plus x times x naught raised to the n minus 2 plus x naught raised to the power n minus 1. As x approaches x naught, that gives me x naught raised to the power n minus 1, x naught raised to the power n minus 2 times x naught, and so on and so forth. And you realize that each term would be x naught raised to the power n minus 1, and there are n of such terms. Adding all of these, we have n times x naught raised to the power n minus 1. And therefore, for every x in R, f prime of x would be n times x raised to the power n minus 1. And we're done. And we just proved the power rule for differentiation. Let us look at 3 other rules of differentiation: the sum rule, the product rule, the quotient rule. Let I be a neighborhood of the point x naught, and suppose that both f and g are differentiable at x naught, and they are both functions from I to R. Then the sum f plus g is a function from I to R, and it is differentiable at x naught, and given as f plus g prime at x naught equals f prime at x naught plus g prime at x naught. In other words, the derivative of the sum equals the sum of the derivatives. And similarly, we define the first derivative of the product fg prime as follows. And there's a little lemma here, not exactly a rule, but it's going to be used to prove the quotient rule. It defines the first derivative of 1 over g as follows. And finally, we have the quotient rule that defines f divided by g prime at x naught as follows. Let's go ahead and prove every one of these. A, we want to prove that the derivative of the sum equals the sum of the derivatives. Again, you have to prove from first principle or using definition. F plus g prime at x naught is the limit as x approaches x naught of f plus g of x minus f plus g of x naught divided by x minus x naught. By definition of addition of functions, this would be limit as x approaches x naught, f of x plus g of x minus f of x naught minus g of x naught divided by x minus x naught. And simple algebra breaks this down to limit as x approaches x naught of f of x minus g of x naught divided by x minus x naught plus g of x minus g of x naught divided by x minus x naught. And by the sum limit theorem, I can distribute my limit over this, and I have this component and this component. But we know that f and g are differentiable at x naught, and the first component is simply the definition of f prime of x naught, and the second is the definition of g prime of x naught. Therefore, f plus g prime at x naught is f prime at x naught plus g prime at x naught, and we are done. Beautiful. Next, let's look at the product rule. F times g, all of that prime of x naught, is the limit as x approaches x naught of fg of x minus fg of x naught divided by x minus x naught. And by definition of the product of functions, that equals limit as x approaches x naught of f of x times g of x minus f of x naught times g of x naught, all of that divided by x minus x naught. And we play a beautiful trick here. We add and subtract f of x times g of x naught. We haven't really done anything because add and subtract that amounts to 0, but very important to us. And using simple algebra and rearranging our numerator, we have limit as x approaches x naught this term and this term, I factorize out f of x. I'm left with g of x minus g of x naught plus this term and this term. I factorize out g of x naught. I'm left with f of x minus f of x naught, all of that divided by x minus x naught. And that would simply be the limit as x approaches x naught of f of x times g of x minus g of x naught divided by x minus x naught plus the limit as x approaches x naught of g of x naught times f of x minus f of x naught divided by x minus x naught. And this follows from the sum limit theorem, also known as the sum property. Therefore, by the product limit theorem or the product property, that gives me f of x naught times g is differentiable at x naught, so the limit of all of these is just g prime at x naught. And over here, this simply gives me g of x naught times, since f is differentiable at x naught, this is simply f prime at x naught. And that is exactly what I was trying to prove. So that is done. And C, which I did say was pretty much a lemma, gives us the derivative of 1 over g prime at x naught, provided that g of x is different from 0 for every x. So 1 over g prime at x naught equals limit as x approaches x naught of 1 over g of x minus 1 over g of x naught divided by x minus x naught. This equals the limit as x approaches x naught of 1 over g of x minus 1 over g of x naught divided by x minus x naught. And simple algebra would give me limit as x approaches x naught of g of x naught minus g of x divided by g of x times g of x naught times x minus x naught. Make sure you still do not have any problems with algebra of this nature. And by the product limit theorem or the product property, that becomes limit as x approaches x naught of the product 1 over g of x times g of x naught times the limit as x approaches x naught. Observe here that we have g of x naught minus g of x. We would like to have g of x minus g of x naught. Again, simple algebra, pull out the negative, and that gives me g of x minus g of x naught divided by x minus x naught. G is differentiable at x naught, so all of this becomes negative g prime at x naught. And over here, as x approaches x naught, this term becomes 1 over g of x naught squared. And my final result is negative g prime at x naught divided by g of x naught, all of that squared. We know that g of x naught is different from 0, and that proves the lemma, which we shall use to prove our quotient rule. Beautiful. Now, D. If g of x is different from 0 for every x in our domain I, let's go ahead and get a formula for f divided by g, all of that prime at the point x naught, which is our quotient rule. We observe that we can write f divided by g as f times 1 over g prime at x naught. We already proved the product rule, so we can use it. So by the product rule, this would give us f of x naught times 1 over g prime at x naught plus 1 over g at x naught times f prime at x naught. And using C, which I did say was our lemma, we do know what 1 over g prime at x naught is. It will be negative g prime at x naught divided by g at x naught, all of that squared. And the second term stays exactly the same. And simple algebra, we put this together to get negative g prime at x naught, add an x naught there, times f of x naught plus f prime at x naught times g at the point x naught, all of that divided by g at the point x naught squared, and that is our quotient rule. So from now on, if I ask you to find the derivative of a function using the rules of differentiation, you are free to use the sum rule, the product rule, the quotient rule, and the chain rule, which we will see later. But if I do say that find the derivative of the function using first principle or by definition, then I want you to actually go ahead and compute for me the limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught. That brings us to the end of section 4.1, the algebra of derivatives, and I'll see you in lesson 15 as we move on with more things like chain rule, the mean value theorem, and so on and so forth. Thank you and God bless you.